This is Jack Jackson. We're going to look in this video about the graphical interpretation of the first and second derivatives. So the basic question we want to consider is, what do the values of the first and second derivatives tell us about the shape of the graph of the original function? So recall that the y values of the derivative are the slopes of the original curve. So they will tell us whether it's increasing or decreasing the direction of the original curve. So if a function has a positive slope on an interval, it's increasing on that interval. So we say it has a positive derivative at a point, it's increasing at that point. So it turns out that knowing information about the first and second derivatives of a function tells us a great deal about the shape and the features of the graph. So let's be as specific as we can about what the first derivative tells us about the shape of the graph. And here we go. The derivative tells us about the first derivative tells us about the slope of the original curve at each point on the curve. The first derivative tells us about the direction of the graph of the original function. So if the first derivative is positive at a point, then the original function is increasing at that point. If the derivative, the first derivative, is negative at a point, then the original function is decreasing at that point. If the first derivative is 0 at a point, then the original function has a horizontal tangent line at that point. We call that a stationary point. Now, there are a couple possibilities. The thing you want to think of is this could be a local extremum. But we can actually look at the second derivative to tell us that. I'll explain this a little bit more in a minute. It's a local maximum if the second derivative is negative. It's a local minimum if the second derivative is positive. And if the second derivative is 0, if they're both the first and second derivative are 0, it might be either a local extremum or it might be an inflection point. We don't know. So we have to do a little bit more investigation. Let me make sure we are clear that we're talking about the first derivative here. Okay? It turns out, if we sort of reverse this a little bit, if a function has a local extremum, maximum or minimum, at a point, then the derivative is either 0 at the point or the derivative is undefined. If the derivative is defined at a point, then the graph is continuous, one connected piece, no breaks of any kind. And we've already seen that it's also smooth, no sharp corners near that point. And if we zoom in near the point on the original graph, it will look approximately like the tangent line, a non-vertical line, near that point. So what does the second derivative tell us about the shape of the original graph? So the second derivative tells us about concavity. Okay, so we're talking about concavity. This is concave up, and this is concave down. And no concavity is straight, linear. Okay, so concave up is like a right side up bowl. Concave down is like an upside down bowl. Okay, so the second derivative tells us concavity. If the second derivative is positive at a particular x value, then the derivative is increasing and the original function is concave up. So let's look at this. So look at the slopes here. Here we have a negative slope, still negative but closer to 0, still negative but closer to 0, somewhere at 0, and positive closer to 0, even bigger, positive, even bigger. So these might be -3, -2, -1, 0, 1, 2, 3 for the slopes, for example. And notice that's increasing slopes. Okay, so increasing slopes means increasing derivative. Okay, and increasing derivative means a positive second derivative. So if the second derivative is positive, then the derivative is increasing and the original function is concave up. Whereas if we look at these concave down ones, that one might be a slope of 5, 3, 1, 0, -1, -3, -5. And so notice that those are decreasing values. That's concave down. So if the slopes are decreasing, that is, the derivative is decreasing, then the second derivative is negative, and we have a concave down function. If the second derivative is 0, we might have an inflection point in the original function. So if the first derivative is non-zero and the second derivative is 0, then the original function has an inflection point. An inflection point, remember, is where it changes concavity. So it goes from concave down to up, an inflection, or it goes from up to down, where we have a point of inflection there. So an inflection point or point of inflection. If the first and second derivative are both 0, then it might be an inflection point or it might be a maximum or minimum. We don't know for sure. We have to investigate a little further. So if the original point has an inflection point, then the second derivative is 0 or undefined at that point. So if we go along a little bit further here, let's look at an example that we might see here. So here we see three functions. We see the original f, we see f prime, and f double prime. And we should be able to tell by looking which is which, but they're also labeled. F of x is the red one. Okay, its derivative is the kind of blue-green one there, and the purple one is the second derivative. So notice some of the characteristics here. F is positive when it is above the x-axis. So this part here, this part right in here, and this part over here to the right of 3. Between 2 and 3, f is negative. Between -4 and -1, f is negative. Okay, but f is increasing when f prime is positive. So see where this one f prime crosses the axis is actually where the original f has a minimum right there. Let's see if I can. So where we have where this one crosses the axis, this one has a minimum. To the right of that, over here, we see that f is increasing and f prime is above the axis. F prime is above the axis, f is increasing. During this portion between here and here, we see that f prime is negative, so that means between here and here, f is decreasing. And we have a maximum right where the f prime crosses, a maximum on f when f prime crosses the axis. When f prime is equal to 0, we have a minimum right here on the original function. In between these two places, notice that f up here, f prime is positive, so that means the original f is increasing. Over here, the original f is decreasing, and we see that f prime is negative. Now let's look at the second derivative. The second derivative is 0 right here. That means right there on the original function we have an inflection point. And so over here, this is concave up, where the second derivative is positive. Where the second derivative is negative in here, then this is concave down on the original function, and of course decreasing right here on the derivative. The derivative is increasing and the original function is concave up when this graph is above the x-axis for the second derivative, and notice that is our inflection point there. Let me erase some of this stuff. We can maybe see this a little bit better again. So let's point out some key features once again of these graphs. I won't write everything on here. I'll just mark a couple of key points. Okay, so notice on the original graph where we have a minimum is when the derivative is 0. So that would be here. The derivative is 0 there. We would also could be a maximum like it is there, and the derivative is 0 here, and so that gives us the same x value, a minimum there. So that's where we have horizontal tangent lines, stationary points. Those are local extrema. Where the second derivative is 0, here and here, those x values there and right here are inflection points. So that's an inflection point, that's an inflection point, that's a minimum, that's a max, and this is a minimum here. Notice that the derivative was 0 And the second derivative here was positive at this point, so that means it's concave up and a minimum. Well, if we have a horizontal tangent line and it's concave up, can you see why that would have to be a minimum? Sometimes that's called the second derivative test. And so we see the original function has a minimum over here again, and notice what happens. The derivative is 0, the second derivative is up here is some positive number. So it's concave up and horizontal tangent line, that makes it a minimum. Whereas right here at the maximum, we still have a horizontal tangent line here, but it's concave down because the second derivative is negative. So second derivative negative says it's concave down. First derivative 0 says that it's a horizontal tangent line. That makes it a max. Okay, and so it gives you some ways of looking at this. So this would be a good thing to practice. We'll be graphing some functions in terms of the the original function, the derivative, and second derivative. Of course, we already talked about how to do this on a calculator, how to put y2 as the derivative of y1. If you let y3 be the derivative of y2, then you can get at least approximations of these graphs without doing any kind of actually computing the formulas. In a little bit, we're going to start learning how to actually compute the actual formulas for these functions.